Hey everyone! Thank you so much for watching another episode of the Weaviate podcast. I'm super excited to welcome Josh Engels. Josh Engels is a Ph.D. student at MIT, where he's done a ton of amazing research on approximate nearest neighbor search. Today, we're particularly going to dive into the window search tree, a super exciting way to improve filtered approximate nearest neighbor search on range filters, all sorts of exciting things we're going to dive into throughout the podcast. Josh, thank you so much for joining.
Yeah, thanks for having me. I'm really excited to talk about this.
Awesome. So, could we even kick it off? Just sort of what led you to approximate nearest neighbor search? What first sparked your interest in it?
Sure. Yeah. Well, I guess I've always really been interested in the whole problem of nearest neighbor search. Like, I think it's a super interesting kind of like this problem, like the intersection of like theory and practice. Like, it's super applicable to like people who are doing like embedding search, which like a ton of people are doing nowadays for like recommendation systems. And also recently with like large language models, like retrieval augmented generation. Um, and so that's why I'm really interested in the problem. And specifically with this like filtered search, I guess it feels like a natural extension of a lot of the base problem of nearest neighbor search is pretty well solved at this point. And so, but there are like other things we need for like those applications I mentioned earlier, like retrieval augmented generation and vector databases. And so that's why it feels like a natural extension of this exciting problem.
Yeah, awesome. I love that line in your paper about the filtering being a key differentiator for vector databases, and certainly kind of one of the biggest early selling points. And we had like vector database versus vector library was you can add filters to the vector search, and it's been such a massive part of this. So I think coming into filtered vector search and helping people understand the difference, I'm really interested in kind of like types of filters. Like Windows Search Tree has a specific focus on range filters and filtering by price in e-commerce stores or the dates of, say, tweets or transactions and things like this. Can you maybe tell me more about how you see kind of the types of filters and filter data?
Sure. Yeah. So one type of filter that a lot of up before our paper, a lot of people had thought about was like categorical filters, which is where you have like 100 different categories for an item. Maybe these are like if you're talking e-commerce, maybe these are like t-shirt sizes or something, right? Or clothing sizes, right? Um, and so it's like this discrete for categories is a discrete number of categories that you're searching over. And there's like a bunch of solutions you can do with this. Like you can kind of one simple thing you could do maybe is you could build like a different index for every category and just search the index you want. When there's lots of categories or like maybe you don't just have t-shirt sizes, but you also have like colors and a bunch of different things. You don't really want to build an index for all these different things, especially if you want to do like ands and ors. But you can kind of do something like lots of solutions do something like similar like morally to this, like where maybe you like cluster things and then you split things up in clusters in different categories, or you first you split things into categories and you cluster within them. So but it still kind of like makes use of this discreteness. And then I think the type of range search, the type of filtered search that we look at is like doesn't use these discrete labels. It uses like these range these like window, we call them window filters. But this is basically where instead of like saying color, you're talking about I want to do like a price range, like I want to return all objects that are greater than $44 and like less than $52 or something, right? You can have arbitrary ranges. um and so that's kind of what we look at, and I think that's fundamentally different. um Excuse me. And then I think those are the most of the filter search. You kind of imagine permutations of these things. Like I want to do some categorical search plus some filtered search, or do and these two together, or them, or really complicated types of things. But these kind of seem like the base units.
Yeah, I thought a bit about like trying to that kind of like Boolean filters. I guess for me, there's kind of this scale of like Boolean filters, low cardinality, high cardinality, discrete filters, and then range filters, and then as you mentioned with the and ors, how you can just smash them together and make that idea of building the index in advance, where you have like just an index for say houses in Boston, if you're like Zillow or something like that, and you've already computed that. And that's definitely something I really want to get into later, is this kind of inverted file index type of approaches and how that differs from this kind of thing. Maybe really quickly before we dive a little further into the window search tree, if we could talk maybe just a little more about the applications of filtered vector search. I see. I really like this kind of like the source filter is how I first got interested in this. Is looking at like you combine these data sources and then you want to search only where, say, the author is a certain value, or say it comes from Twitter compared to archive. And maybe just we've talked about kind of the the color of t-shirts. I'm just curious if there's any more applications, any more thinking about that motivates your interest.
For Windows search specifically.
Yeah, that would be great.
Yeah, I think there are lots of natural, like the biggest ones I think are probably price and time. So
Yeah.
time I think especially is pretty big, like um because yeah, like so you might imagine, like, you could categorize time. Like you could say, like, this is what Google does. If you search on Google, you can search by like 1 week, 1 month, 1 year. They also, I think, you can make it custom time ranges, but
Yeah.
the default is like these set time ranges. So I think that's, yeah. So being able to, so this is like a very like many data are stored as like time series, or like are naturally time series. So being able to search over like a specific time range and then do nearest neighbor search within that time range. This is actually one of the main applications we look at in our paper.
Yeah.
Is like super valuable, and I think like a really great natural use case. So that's the biggest one, and then I think, yeah, there's other. This, it seems like there's other many natural cases, like I mentioned price. You want like your own specific price range. Um, yeah, I'm sure there are other ones. Like I mean, the nice thing is it's like a general tool, right? Like maybe you can imagine something really weird, like scientific data or something, right? Like maybe there's like these like real number categories, like astronomical observations or something. Although that's just really speculating. But definitely, I think time is like a supernatural natural continuous quantity.
Yeah, I really like that one. I mean, like the just searching for my tweets from July and how that can become a continuous range. But then that also kind of makes me think about like is July like a category, and then I have like 5 years of 12 months, and so thinking about that range really interests me. And generally, I think just it's really important to kind of motivate these applications, explain filtered vector search. I know it's so interesting to, maybe I'm going on a bit of a tangent right now, but just meeting you and seeing your paper on Windows Search Tree, and I think there are only so many papers out there right now really getting into the weeds of filtered ANN. I would say there's like 15 or so, but yeah, so let's dive into it and get into the
Sure.
details of it.
Yeah.
So can we kick off with maybe an overview of what the Windows Search Tree is?
Sure. Yes. So let me the yes, the basic idea is, we want to build an index that can allow us to answer these like approximate window search queries efficiently. So what a window search query here is basically, it's a nearest neighbor query. So a nearest neighbor query is where you have a bunch of points in your data set, and you want to find the closest points to your query. And it's approximate, so you can return the approximate nearest neighbor, right? Um, so, but a window query basically adds an additional like starting and ending label, and you require like the you want to find the closest point subject to, that its labels within this A and B. Um, so this is what we call like a window query. So, and then we want to build an index that can solve this efficiently. So the way that we do this is, so the kind of the first way, the simplest way we do this, is, oh, I guess let me talk about some naive baselines you could do. So one thing you could do is you could do queries, like you could query 1 point. You could just do a query, right? You query the top 1 point, and you see what's within your filter range. And if it's in your filter range, great, you win. If it's not, then you say, okay, I'm going to query the top 2 points and then you see if it's within that filter range. And then maybe you query the top 4 and the top 8 until you get a point that's within your filter range. So we call that post-filtering, because you're doing the query and then filtering afterwards. Another thing you could do is pre-filtering, which is basically where you have a list of all the points sorted by their label, and then you do a binary search to find the start of the label, and you do a binary search to find the end of the label, if you find the end of the range.
Yeah.
And then you loop through all those points and you find the nearest neighbor. So this is what we call pre-filtering. And intuitively, pre-filtering works well when there's not many points that meet your label constraints. I think you call that low cardinality. And post filtering works well when there's many points that meet your filtering constraint. So that's high cardinality, I guess. So it's in the middle range that neither of these baseline techniques work well. So this is where we start to introduce our solutions. Does everything sound good so far?
Oh yeah. I guess I just one thing like I think usually in the papers when you talk about pre-filtering HNSW, you kind of refer to, and I found this to be an interesting thing as I was digging into Acorn as well, where pre-filtering might refer to, say, a node is allowed in the candidate set, but not the result set as you traverse the
Mm,
proximity graph. So I
I
think
see.
this is like maybe a slightly different use of
Yes.
pre-filtering. Yeah.
Slightly different use of the word pre-filtering. Yes.
Yeah.
Yes. In our case, when we get into it, yeah, we won't have any restrictions. Like, so this would be like when we're doing post filtering, when we're like, doing this post filtering technique. I think what you're saying is that there's a distinction of whether or not points that meet the label are allowed in the candidate set or not. When you're traversing the graph, we don't make that distinction. Whenever we're doing post filtering, we always add any point to the graph. It's just not an optimization that we like explore. But yeah, so good clarification.
Awesome. Yeah. Awesome. Yeah. All set though. But yeah. So now so now I think we're getting into, now we're building the tree, and this is kind of
Yeah.
yeah.
So yeah, sorry, I hadn't gotten to the tree.
Right.
I was just trying to I was just setting the stage with like these pre-filtering and post-filtering. Okay, so yeah, now the tree. So now our data structure is basically a tree where we build an arbitrary ANN index. Here we use disk ANN in our work for basically the points with like all of the labels. So that's the top level of the tree, just in a whole ANN index. The next level of the tree, we split that in half and build an ANN index on the first points with the first half of the labels, like sorted labels, points with the second half of the sorted labels. Then we split it in half again and build points with, so then you have four indices, each with 1/4 of the labels. And you keep going all the way down till the bottom. We like have a cutoff of basically like 1,000 points. So we don't make indices smaller than 1,000 points. And then when you're doing a query, you 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 basically have your label range. And it turns out that it's not so hard to show this. In fact, this is like related to segment trees, like a classical data structure that you can basically, is like a unique split that you can combine these like these intervals that were built up in the tree into like the whole query interval using like a logarithmic number of intervals. So intuitively, what you do is you take the biggest thing that fits in this interval, and then you're left with two little chunks on the sides, and then you take the biggest thing that fit in those, and then you're left with little things on the side. And so every time you take a one that fills it up, you're splitting it by at least half. So you end up with a smaller and smaller things on the side. Um, and so at the end of this, you're going to end up with a collection of indices that basically, whose union, in fact, your disjoint union of the labels equals the entire label range that you want. And then you can query. So each of these indices only has points in the label range that you care about. So then you can query each of these indices and find the top, 1 point or 10 points or whatever you want. And then you just take you do that across all the indices in the range, and you just take the best 10 across all of those, the top K across all of those. Yeah, is that, and the neat thing about this is that like you don't need to a priori choose like a size of range that's like good that your index is built for. Like any part of the tree will like it's kind of like scale agnostic. Like any width of label range will always take a logarithmic number of indices to answer.
So I think my first question is about when I was reading through your related work section, and you touched on the CAPS method, which it sounds like does something like this, but with a Huffman tree. So I was curious about how the data distribution is used when you're splitting the nodes.
Right. Yeah. So I think I found so caps. I don't think it's caps that does that. I think it's a different piece of related
Oh,
work.
sorry,
I
I'm
think
not.
caps
I
does.
just know
No,
it
no,
from
you're good. You're
the
good.
sitens and
Yeah,
the.
no, you're totally good. I wrote this a few months ago now too, so I could totally be wrong. Um, yeah. But I think, yeah, one thing is that like the data, we don't need to make any assumptions about data distribution, which I think is like the really cool part, right? like and with this something prior work had to kind of assume they were like doing some sort of like warm up stage where they were trying to learn the data distribution or something. Yeah, well, what we're doing is like it's we're just splitting. So you just sort the points by their labels, and then you like basically use that sorted list to like figure out how to split these things up. But there's no requirement like the only like there's nothing about data distribution in there basically. Like we don't whatever data distribution we have will work. And in fact, in the paper we have like this adversarial case that like this method works very well against. So yeah, so this yeah, there's no yeah, it's data distribution agnostic basically. Um yeah.
Yeah, so maybe just to clarify, so if I let's say it's $1 to $100, and I split and I go 1 to 50, 51 to 100, and so now that I'm in 1 to 50, let's say like 80% of the points are greater than 45, would I still split at 25?
No.
Oh,
No, you would split at 45. Yeah.
okay,
Or you
very
would
good.
split at
Or
no,
some
sorry,
yes,
you
some of
split
the
at whatever the exact middle was. Yeah.
Yeah, yeah. Okay, super cool. And then so that really motivates me to ask this question about like batch construction kind of, because I know with disk ANN is this approach where is batch construction where you have all the nodes and so you randomly connect the graph and then you prune it, compared to HNSW, which is like you incrementally build up the index.
Hmm.
And so I imagine, the batch algorithms probably pair really nicely with this, with the way that you're going to, understand that 45, that 80% are at 45. I've already forgotten the numbers I said, but so do you think this algorithm works particularly well with kind of batch construction methods or
Yeah, interesting question. I think it's it's because like so basically you can build this whole tree before you start building any of the indices, right? Like because building the top index doesn't actually like give you any information you need to build the other indices, right? um so like you can just give me all the labels and not even give me the vectors representing the points, and I can tell you how they're going to be split up.
Gotcha. Yeah.
And so once you have all these splits, you can just build all the indices in parallel.
Oh,
um so yeah, and then each index you can build it however you want.
yeah, I find that part to be so fascinating. And I saw, we were super lucky to have Magdalene Dobson on the Weaviate podcast, and I also met her at MIT, which is the coolest thing that. But and I saw your paper builds on the Parlay ANN, the implementation. Maybe I think we were maybe going a little tangential to the algorithm, but maybe if we could talk a little more about how parallelism is used here and just the details of what
Yeah,
Parlay.
sure. Yeah, so I guess yeah, basically we were using the Parlay ANN repo, which has all these algorithms implemented in parallel, like disk ANN implemented in parallel. Um, and then yeah, it's nice because our implementation is also written in C++. So when we're building our index, basically we can build all of the sub indices in parallel, and so it doesn't matter too much for like the top indices, right? Like or it actually matters there too, I guess. The very top index is just one, so it doesn't really matter if you just had that.
Okay.
But yeah, even like even if your tree's only like has two like two rows to it, right? Like the top one and splitting the next two, like building in parallel, right? Will probably allow you to build this whole tree like almost 3 times faster or something, because you're building all the indices in parallel. So that's one really nice thing, is that it allows us to build all the indices in parallel. Another really nice thing about writing C++ is that we can reuse. So basically, to build these graph based indices, right? You have the graph and you have the vector store, right? And the nice thing about doing it this way is that we can in C++ is that we can use a single vector store for all of the indices, and just have a
Oh,
different graph for every index.
oh, got you.
And so this basically allows us to use a lot less memory than we would otherwise. We don't have to duplicate the vectors, log n times, however the size of the tree.
But then don't you have to bring the vectors, like how you bring the vectors into memory? Does that maybe become more complicated?
No, it doesn't. No. So all of the vectors are stored in sorted label order on in memory.
Got you. Okay.
And then each of these indices has like a view of this sorted list, basically a non-owning view. and then they can just treat that as their vector store. So sure, like if you have uh, like probably if you're doing lots of queries in parallel, right? Like this there might be the like overlapping views like in different like L1 caches or something, but like that's fine.
Yeah. Okay, I'll be honest, and I can't quite keep up with this part of it.
No,
There
yeah,
was
don't worry about it.
there was one of our podcasts, Eddie and Dillacker, the CTO of Weaviate. They implemented like brute forcing from disk, and it's something about how they encoded on disk that I still haven't wrapped my head around quite how all this
Okay,
stuff
yeah,
works.
yeah, don't worry. Just to be clear, there's no disk part happening here, so maybe that makes it simpler. It's just stored in memory.
Okay, but you still have something kind of like how you sort the addresses, or something like that. Like you still put them together. Sorry.
So you just sort the points by their label. So like point one, like say you're sorting by price, right? You sort the points by in memory by like the lowest price first and the highest price last. And
Yeah.
then because you're splitting in the tree
Oh,
based
okay.
off this sorted order, then each indices points are going to be like just chunks of this array.
Got you.
Because like if somewhere in this tree, if you're an index, your points are always some like what's the word, like some consecutive subsection of label space. Like I'm always representing the points that are like greater than $42 and less than $56 if I'm an index, or greater than $12 and less than $20, and that always corresponds to like a consecutive uh, section of the points in if they're sorted by their labels.
Yeah, amazing. So I'll definitely be rewatching this, and everyone listening, anyone interested in database engineering and this kind of stuff, these are the details. So I did have one other question kind of about memory before I think we'll come back to the Windows search tree. And I wanted to ask more about the post filtering, which was
Yeah.
the kind of coming to the inverted file type of approach where you sort of build the indexes for particular filters in advance. I've always imagined that now you have this problem of maybe you store that extra index on disk, and then like the query wants it, but now you need to bring it into memory. But then, and as we talk about like AND filters, there could be just so many different filters that you combine like this. And so, but maybe there's some kind of query optimization where you know the workload and you know which ones to bring into memory. And so I guess maybe if I could ask generally, like your thoughts on the inverted file and the kind of partitioning the nodes, so you kind of like compute the set membership of which nodes are on the filter in advance. It's kind of like this range filter thing. I think. Yeah. Is that?
Yeah, I'm not totally sure. Sorry, I'm not totally sure I followed the question. Are you saying
Yeah.
well, let me see if I can. You're saying for like these inverted file indices, like this is we're talking about categorical search, like where or just normal inverted file indices where you just I guess for just so we're on the same page, I guess I can just restate like kind of so like an inverted file index. I guess the way I think about it is you have like one a really simple thing is that you just cluster the points using k-means clustering or something, and then basically you to do a nearest neighbor query, you find like your k closest clusters or something, and then you just do brute force search across all the points in your k closest clusters. Is that was that what you're thinking of?
Yeah, but like doing that for color equals blue.
Oh, sure. Okay. So I guess okay. So then there's like this is what the CAPS paper I guess is, or like then so
Yeah.
then the question is like if you want to add a category, one thing you could do is you could within each cluster split things in different categories, and then when you reach a cluster, only search the points in your category. And then another thing you could do, you could like do the opposite of that, and first split all the points by color, and then do it within each thing, like do a bunch of individual, like then do k-means clustering within each category. Um, yeah. So yeah, my co-author Ben Landrum on this paper, Caps is his or no, I think Caps is sorry, I think I got confused here. Caps is also does this, but Ben's work is called like IVF something. But yeah, they won like the filtered ANN competition at
Yeah.
NeurIPS this last year. So but yeah, they do something they do something like this.
Yeah, and sorry the question wasn't well read in,
No,
but yeah,
that's okay.
that kind of IV.
So
Yeah.
did you have? So I guess another one. I think we're on the same page. What was the question? Sorry.
Yeah. Well, so yeah, I really like the IVF squared kind of idea, but then
Yeah.
but then it's like you have to have the nodes in memory, the index in memory for it to be fast, kind of, right? You don't want to have to every time you say color equals blue and price is, $10 to $100.
Right, right.
Yeah,
Yes, yes. So yes, I think that's a big problem with filtered search because you're basically duplicating the index a bunch of times at the end of the day, right? When you're doing the like reclustering or something.
yeah,
Um, although yeah, I don't totally know the details of IVF square. I know for our setup, you have to duplicate the index a bunch of times. And I think Ben told me you had to duplicate the index a bunch of times for IVF squared too. Um, but I'm not totally sure about that part. But yeah, I guess yeah, memory is like definitely for our indices, like they're like because of this like duplicating because we have to duplicate every row of the tree, right? You get like a I don't know like a 3 or 4 or 5 times memory blow up, which can be a lot. Um, and yeah, so one thing you could try to do is store it on disk, I guess, but I'm skeptical that you can make it fast enough to make that work. Maybe you could, but I feel like having to like load entire indices from memory feels expensive. Though that being said, I do know like disk ANN, right?
yeah,
Uh, has disk in the name. Like they do this, right? And
mhm,
it seems to work. So
yeah,
so what you could do is for every single node of the tree, just have a disk ANN index that stores most of it on disk, and then do like a disk ANN query. I like feel like it could be slow because I mean I just as like a engineer, I'm always worried about putting things on disk because I feel
mhm.
like you have to like it takes a while to read from disk. But um, yeah, that's not my. We didn't do it on disk. Ours is just in memory, and I guess Uh, I don't really know enough to say about I guess it. Yeah, I don't know. Assuming disk ANN made it possible to put things on disk, like because it's just a bunch of disk ANN indices at the end of the day, you could probably make ours on disk too.
Yeah, super cool. And I'm definitely I'm not like like able to completely understand in our conversation how the in memory works with the sorted tree, but I'm sure like I'll get it later and have a better sense of this question.
Yeah, yeah,
But yeah, so kind of transitioning a bit, and I definitely do want to come back to kind of the memory requirements of the Windows search tree and see if maybe we can tease out any ideas there. But I think kind of finishing out the Windows search tree algorithm, can you tell me more
yeah.
about optimized post filtering and super post
Yeah,
filtering?
yeah, yeah. I was excited for you to ask about this. Yeah, this is quite cool. Um, so yeah, in the Windows search tree thing I mentioned, right? You have the top level, and then you have you basically split it in half and you split it into quarters, right? Um, and then you basically choose some of these cells basically to build up the whole query range.
Yeah,
Um, but another thing you could do, so this works and this is great. But another thing you could do is you could. So we talked about post filtering, which is where you basically take the whole set of points and then do like this like doubling based query in it till you find like enough neighbors to return like one of your like a filtered point. Another thing, but this is like pretty bad. Like, say you have a really tiny filter range, right? This like low cardinality case, right?
mm,
You're gonna have to do a lot of doubling, and it's gonna give you really bad recall. Um, so instead, what you can do is we have this whole tree now, right? So you could choose the smallest range that fits your query range. So out of the whole tree, right? You could choose. So say you're like some super tiny thing. There probably is like something that's a little like some query range that's a little bit bigger than this that like fits your query, and then you query that one. You don't query the whole thing, um, and so that's a lot better.
mm.
Um, However, like you could get really unlucky. Like, so we have here and we split in half, right? Imagine your query is directly in the middle. It contains like the 50.1 percentile point and the 49.9 percentile point, right? These two
Mhm.
center points. Then all the splits are going to exactly split on this exact middle thing, right? So you'll never be able to actually do this query. You'll have to just do it on the top one. That's the only one that contains um, that's the only one that basically any query that goes across the first split will have to query the top one, no matter how small it is. Um, and so instead, what you can do is this is what the super I think we call it super optimized post filtering or something in the paper. So instead, what you can do is you can change it so that instead you split into two, But then you also include another index that basically like spans that gap, that like goes across that gap.
Oh,
So you have like um you're basically adding more indices to like span these gaps, scan these like what would I call them? Scan like the I don't even to basically span like the when two bricks are together. There's like that I forget what you would call it, like the line between the brick, right? You're like putting like another brick of the same size like directly like in the middle there, so like nothing can like slip up the tree. And if you do this, you can kind of prove that like that the worst case blow up factor, we call it, like the ratio of the size of the query range to the size of the index range when you take the smallest one that contains it is like less than like 4 or something, depending on exactly how you build it. So instead of being before, it was like it could be order of n, like the blow could be order of n. You have a constant size range, but you have to query the biggest index. Now we've limited actually to a constant size worst case blow up. And in practice, this helps a lot.
awesome. Oh, so sorry if I'm slowing it down a little bit.
No, no, no. I realized that when I started talking about bricks, that it might have been totally impossible to understand what the heck I was talking about.
That was great. I understand if we just like pretend it's uniformly distributed from 1 to 100 to keep it easy, and then I understand this problem as we split on 50, and then we've got 25 to 50, 49, 25 to 50, and then 50 to 75. Let's just say it like that. And then I have the query 40 to 60 is the interval that I'm querying on.
Exactly.
So I imagined you just search those two sub. So something that I got lost on is when you said you would have to go query the top, the root
Right.
node, because I was
So
thinking that you could.
yeah, this is a
Yeah,
perfect example, like with the 1 to 100. Yeah, say you just have like 100 points, 1 to 100 or something, right? Um, so what super optimized post filtering does is say your query range is like 40 to 60, right? Like you said, then it has to find the smallest index that contains the range 40 to 60,
yeah.
and then it's going to do a post filter. It's not going to query 2 indices or something like that. It's only querying 1 index.
Oh, okay. Oh, interesting. I thought there was like a bubble up where you search two and then merge it. That's just not a right understanding. All right.
So it's crazy because we have like lots of algorithms. So one of the algorithms searches. Okay, so the original algorithm, right, just builds up things inside this. Like if you're building 40 to 60, you're querying a bunch of indices that are within 40 to 60. Like you're probably querying like 45 to 55 and like 55 to 57 and like 57 to 60 or something like inside this range. And
Yeah,
then post filtering only queries 0 to 100, right?
yeah.
Like normal post filtering, like the baseline.
Ah, okay.
And then our approach only queries the like the smallest range in the tree that contains 40 to 60. And in this case, because the first, when you split 0 to 100, you get 0 to 50 and 50 to 100, like already 40 to 60 is across this, like, is across 2 indices. And no matter how many times you split, it's still going to be across at least 2 indices. So the smallest thing that contains it is 0 to 100.
Okay. But I guess yeah, I don't think it would be accurate to say because also because of how the ANN search is scaled logarithmically. So searching that bigger index would be faster probably than searching the two smaller ones and combining the results. Is that also?
Yeah.
Yeah.
Also, yeah. So like you could. So actually, there's another thing we do called like the 3 split. It does something like this that you're saying, where you find you find like the largest index within your query range, and then to do the size, you do like you do post filtering based off that, and this guarantees that they're not too big. Um, so this is like another thing that we do. Um, yeah, but that's probably, we don't have to go into that, but like I think the super optimized post filtering is like a really neat idea. Like so I guess okay, but just like so yeah, does it make sense to optimize post filtering thing, like why you can have these kind of worst case situations?
Oh, I think I understand the worst case situations. Kind of like my curiosity is now thinking like, so you're post filtering in the sense that you try to take like 1,000 to then filter down to like say you ask K for 100 search results, and now you need 100 where color equals blue. sorry,
Mhm.
or where price is, $45 to $50,
Sure, sure,
and
sure.
yes, it doesn't matter. But so it's like, how many do I oversample for then post filtering? Is that like, because you now with post filtering you're going to take 1,000 to filter down to 100. No, not
No, that's
oh,
right. So um, so yeah, say you want to find like 10 points that meet your, like you have to find the top, you want to find the top 10 points, right? Like they could be so yeah, so basically, like I guess this question is like, how do we do post filtering, right? Like given a certain index, and that's kind of like the implementation detail doesn't matter too much, but the way we do it is like this doubling technique where we search for like 10 points, see if they're all meet our constraint. Then we search for like 20 points, we see if they meet our constraint. There are other ways you could do post filtering, and like other indices do other types of ways. Like you can imagine like some dynamic search that keeps on searching for more points until you get 10 points that meet your filter constraint. Um, but we do this kind of doubling technique. Um, but this is kind of like this is like kind of, I guess, not the interesting part of our algorithm, I guess. Like it's just kind of like the interesting part is like how are you like combining these different indices in the tree into like a single search.
wow. And I guess when you're then doubling and retrying, can you maybe save some parts of the previous search? Like
You could, yeah. We don't do that though, but you totally could. Yeah, I guess like this is like not a vector database or anything implementation, right? Like there's probably ways you can make this more efficient. Um, but yeah, we just do this doubling thing. We don't like reuse anything from before. I did try like at some point trying to make this more efficient by like making it like dynamic, like I mentioned, but it was like taking a lot of time and didn't really seem to be going anywhere super fast. So we just kept it with a doubling implementation.
hmm. Yeah, super cool. All right, awesome. So that was such an awesome dive into this post filtering thing. Sorry, my brain is like sweating extra trying
No, no,
to.
you're good. Yeah,
But awesome. So could we transition into kind of the state of ANN benchmarking, the data sets used to measure these algorithms?
sure. Yeah. Yeah, I can give like a quick rundown. I'm sure lots of other guests have talked about similar stuff. So there's kind of, I guess, a few different aspects of this. So one thing is there's A&M benchmarks, which are small-ish data sets, about like a million to 10 million, um, made by it is made by this ex-engineer from Spotify. I think his name is Eric. I forget his last name. Um,
Bernardson, give him the
Eric,
shout out.
yeah, yeah.
Also an
So kind
advisor
of
of
like
Weaviate.
what did you say?
Oh, as also an advisor of Weaviate.
Oh, he's a memorizer. Weaviate. Great, great. Hey, Eric, if you're listening. No, but he's really great, right? I mean, he was like one of the first people who like really looked at ANN like this, I guess, scientific way, and like I believe was working at Spotify when he came out with these benchmarks like 10 years ago or something. And that spurred like a bunch of research into. I mean, that was not the beginning of research into ANN. Like we had like LSH, the fast sublinear nearest neighbor search algorithms like back in the early 2000s. Um, but this was, I think, what spurred a lot of like industry interest and people building like fast ANN algorithms and like comparing against each other and like looking at leaderboards. Um, and so that's still there. Like people still do this. Like Google came out, like I guess now probably like a couple of years ago with like ScanN, which is like
Hmm.
which like was like better than, like it was like cool because it was like a new algorithm that was like better than these old ones. Although it nothing. I mean, it didn't use any like crazy new novel ideas. It was just like combining ideas in like really clever ways. Um, so that's there, but I guess then more recently people have said, well, okay, like it seems like we have really good algorithms for these like medium sized data sets. Like let's look at big ANN, right? So then
Hmm.
this is like big ANN benchmark, which is like has been a competition at NeurIPS like the last few years,
Yeah.
where people are looking at like billion sized data sets, and then also at like different types of data sets. So the last big ANN benchmarks, we had filtered ANN, which like IVF squared did. We had like streaming. We had like I think we had like memory constraint. I'm not sure. Maybe one or two others. Kind of these like fun alternative categories that are kind of more like maybe like even more getting to be more like real world or more like different variations of the problem that are like relevant in practice. And so I think the benchmarking infrastructure for this stuff is harder because there's like more, it's different types of problems and they're bigger data sets. Um, so like I know Harsha, the guy the person who runs the competition, like has to do a lot of work for these competitions because like working with people to get their solutions to work, and they have to use and it's just like a lot harder. So I don't think that's like has reached the same level of standardization as the original ANN benchmarks. Like you can't just there's no like updating a leaderboard like there is for ANN benchmarks where like things will basically do it automatically or something like that. And then so that's there. I guess that's the other main benchmarking open source thing that people look at. And then yeah, in our work, we use some data sets from the original ANN benchmarks, and then like kind of add synthetic labels, and then we come with our own data set that's based off like red caps, which are basically a bunch of images from Reddit and Imgur, I think, that have timestamps, which is nice. And then so we basically run those through an image model. I think we use Clip, and then take the embeddings from those and along with the timestamps, and that's like our data set. So this is kind of like a real world example. But yeah, as far as we knew, there was no A&M benchmarks for window search. So we had to kind of build our own data sets.
Yeah, it's so interesting. I love how you said the like kind of almost quirky types like out of distribution,
Yeah,
streaming, sparse,
yeah,
and
exactly. Quirky, yeah, exactly.
and yeah, kind of something I said earlier is I find it to be very fascinating that I think there's like 15 or so papers in filtered ANN, and I think you're in like a handful with Ben and Magdalene and
Yeah.
Liana of like the world's leaders in filtered. It's so cool like being at the forefront of this new thing, because I think kind of one other thing I wanted to touch on is like scaling it further. Like what we've seen at Weaviate is once we scale these like crazy, the vector indexes, that's when the slowdown of slow filtered
Mm.
search with just the pre-filtering HSW, that's when we started to see. And yeah, I think it's just so interesting. You're talking about the ANN benchmark server, and yeah, I guess just thinking about how people are going to scale up these tests and then interface their systems with maybe like Docker and things like that is some things we're seeing. Yeah. So one question I have about data sets with filtered particularly is the correlation between the filter and then the vectors is something that's maybe being raised as something that's very important. The Acorn paper does a big detailing of this where they show basically like if the filter has some kind of correlation with the vectors, like the semantics. So if it's image embeddings and the filter is maybe brand, like if it's like Nike, then
Hmm.
the vector embeddings for Nike might also sort of be in the same vector space as that filter.
Mm.
Is this
Yeah.
something that interests you? Yeah.
Yeah. So I guess I could talk about this. Well, so like in relation to our paper, right? In relation to like window filters. Um, like so yeah, the post filtering methods suffer a lot when this condition of independence between the labels and the vectors are not satisfied. So like we have an adversarial data set
Yep.
that make these methods perform poorly. On the other hand, like the original method, the thing that splits up into these uh like a basic chunks it right from the inside out, that does not suffer in the same way. And it's like basically like it works in the adversarial data set. Like it works no matter what the correlation between the labels and the vectors are. So at least in our data set, we definitely like play with this idea and look at it carefully. And the interesting thing is that like the other methods that don't suffer this thing, like they're faster in a lot of the other cases without if the data are independent from the labels. Um, in general, I think it's interesting to think about like, uh, can you build? Because in our case, right, like we have this one method that is really decent, like really well on like any correlation, and you have another method that suffers
Mm.
when it's not independent, but does really well when it is independent. I think it'd be interesting to think about like you have data dependent LSH, right, which
Yeah.
basically like get better if it adapts to the data set, the distribution. So it'd be interesting to think about methods that like do better when they're correlations, because we don't neither of our methods do that, and I don't know what that would look like, but certainly you can imagine like some sort of like learning based approach, right?
Mm.
Where maybe like, yeah, you have some sort of like, if you I guess this is, there might be other work that do this, where if you know like the query distribution or something. But yeah, like being able to make use of like structure in like the label, like similarity of the labels and similarity of the vectors, I think could be interesting.
Hmm. Yeah, I don't have like a quick comment to that. I agree fully, and it actually it kind of really inspired me thinking about this. I hope maybe our listeners too, and this isn't too much of a tangent, but it makes it kind of earlier our discussion about how Windows search tree is targeting range filters, and then maybe you have maybe some other algorithm is better for a Boolean filter or look. It's like do you think that the ANN algorithms will differentiate for each of the kinds of filters? And this There's kind of another
Mm.
silly thing is even within a low cardinality filter, like let's say it's a Boolean filter, you could have a 50-50 distribution, or it could be like 5%, 95%. And then it's like, do these require different algorithms or just hyperparameters on the same one?
Yes. Yes. Interesting question. Yeah. I guess in terms of the like actual ANN algorithm, my hot take is that like that will basically be like, that's like basically commoditized almost. Like at least in our work, right? The actual ANN algorithm that we use for the nodes of the tree doesn't matter, right? You can use anyone. You can use the fastest one that you've got. We use like, ParlayANN, DiskANN, because it's like it works well, but anything will really work, right? So it's kind of plug and play. I think this is true about some of the filtered stuff. Um, so I think in terms of like the actual ANN index, that's my hunch that like long term, like this is the most natural way I think to think of this stuff, because like it allows you to swap in new ANN indices for different problems, or if the ANN indices get better or something. Uh, and then in terms of sorry, I forgot what the other part of the question was.
I guess I'm just curious so I might use Windows search tree when I have range filters,
Yeah.
but say I would use Acorn when I have like I'm going to be combining categorical filters on the fly, and so I'm just curious,
Mm.
yeah, like how different, like if I mean, could this kind of come selfishly from Weaviate, where it's like how many of these do we need to implement? Like, how,
Yeah. I guess my hunch is that like these things will probably stay separate. Like probably. I mean, you could imagine like there are systems that try to do all of these things with kind of like one structure, right? Like basically the type of like, there's maybe you could have like some tree based thing that works for everything, or some like post filtering that like queries the graph and like continually adds things as it searches the section of the graph it's in. That would work for any like arbitrary filters. Like you have a function that's a filter that returns yes or no for every point, and it could run a machine learning query or something, right? So like for these super general things, I think you can build that sort of system, but I don't think it'll be as good as the specialized methods. So I guess I kind of imagine it like a database, or even like pandas or something, like Python pandas. Like if you're doing some like atomic, like some like operation that's like implemented, that has an implementation, right? Then you use that. So like if you're doing like a Windows search query, maybe you use the tree we built. If you're doing like a categorical search, you use like IVF squared or something. But then if you're doing like some arbitrary like thing where you're like, yeah, for every single point, in order to tell in order to tell whether this point meets your constraint or not, you take the embedding and you run it through like a machine learning and like the machine learning model, right? Um, if you're doing that, then like you have to use some general thing. So I guess that's kind of how I envision like the future of ANN vector databases. That like there's like these basic operations that have like these like purpose built implementations, and then if you're doing like your own custom thing, then you use some general case. And maybe one day the general case will be good enough for like these things, but I don't see that right now.
Yeah, I also kind of agree with that vision. I really liked we had Andy Pavlo on the Weaviate podcast, who's a database professor at CMU, and he started this company called OtterTune, where they're like tuning for the workloads and kind of learning about query optimizers. I think that kind of thing will play. So a question I'm really curious about is so with the Acorn method, they're trying to change how you traverse the subgraph. So if you have a proximity graph, then you say you have a subgraph that's induced by the filter, And so I'm very curious if we can take these, subgraphs that we build through the tree, and if we can like put them back into the main graph, like just have one graph, and then you just kind of filter search. So I think with Disk ANN, they already have this kind of thing where you build the graphs separately
Mhm.
for each of the filters, then you merge them by just connecting the neighbors. And so I'm curious if you can maybe just take all. Yeah, yeah.
Yeah. Um. Oh, sorry. I guess I'm sorry. I didn't mean to cut you off. So what was the question? Was like sorry.
Oh,
Sorry. So
yeah,
what
yeah.
was
So if you can maybe like you build all the tree, you have all the indexes for the trees, and maybe you can just merge them all into one graph by just union of the neighbors.
yes. Like for when yes. Um. Maybe. Uh. This would be a cool idea. We thought about it a little bit. The reason it doesn't work naively with disk ANN because like disk ANN starts from the same position every time, right? And so you can imagine for like these smaller graphs, like say you're in like some super specific section of the space, even if you're merging it together, right? Like I guess you're saying you have still to start at a point in that space. But so okay, so say you even start at a point in this like ball, right? Because of the way we build disk the way the disk game is built, like it's kind of built coming out from the center section. So it wouldn't quite work naively, but yeah, maybe say you have like just some uh okay, so say you're not using disk ANN, like you're using like some like you can even imagine a simpler algorithm where you're just some graph where you're like do like it's like a KNN graph with like some pruning or something, and then you're just combining all of these together, taking the union of all the edges, and then just searching over these subgraphs. Um, I think that would work. Um, yeah, I think that would work. I guess one actually it wouldn't. Okay, no, I take that back. It might not work because uh, there might be too many edges on some of these nodes. Like you're combining all of these edges together. Some nodes might have many edges. Um, but maybe that would be. I guess okay. Here's my thought. You could do this, but I think it would be the same as the tree would have. I'm not sure it would be like you might use a little bit less memory. Some because some of the edges might appear in multiple trees, so you would get rid of that. In multiple nodes, you would get rid of that.
Hmm.
But so maybe you use less memory, but it's still kind of like the same. The query process would still look similar, I think. Um, but yeah, I guess I have to think about this. I think it's a nice idea, and probably if you could maybe simplify the index a little bit if you did this.
Yeah, I think I agree with you on the. I don't know how much it would speed it up, but I think it might just make the. Oh yeah, I'm not sure. Just kind of
It could
throwing it
make the
out there.
memory less. It could make the memory a little bit less. No, it's a nice idea. It's a nice idea. I think it's like not. It's not trivial to do this, but
Yeah.
like it doesn't seem like it doesn't feel like super difficult. Like it's probably possible.
Yeah, super cool. Awesome. Well, Josh, this has been such an amazing coverage of the Windows search tree algorithm. I wanted to really kind of sort of end with firing two quick questions to you, where I don't really know too much about these topics, so I won't be able to keep the conversation. But just kind of quickly rounding it out as one of the world's ANN experts. The first thing is,
God, I don't know about
yeah. But so the first question I have is about your work building on ParlayANN, and I'm just so curious about this kind of like hyper-threading, multi-threading with ANN indexes, and particularly Magdalene gave us a wonderful coverage of multi-threaded index construction, and I'm very curious like with multi-threaded querying as well. Particularly things like NVIDIA has this CAGRA index where they describe how they are going to search with a proximity graph on GPUs, and so it just makes me think like, what does like a massively parallel vector search look like? Yeah.
Yeah, good question. So I guess one thing is that like parallelizing batches of queries super easy. It's super easy because you just do it. The index is static. You just do a different thread for every query. So the I guess the interesting question is parallelizing a single query. Um, and I'd say if there's a few things about this. One is that most of the time it's probably not necessary. Like these large these like even big graphs take only I don't know like probably less than 10 or 20 milliseconds to execute a query, which is usually fast enough.
Mhm.
But maybe there's cases where, for example, if each vector is very, very long, then doing a single distance computation is very expensive. And so maybe the query will take longer. So maybe you want to parallelize it in that case. Um, and I did look at this a little bit with, we were talking about it with Julian, my advisor, Julian Shun, who thinks a lot about parallelism. Um, and yeah, basically someone did this actually. That's the moral of the story. Someone did this like a couple of years ago. I love to link to the paper, but I forget what it's called. But it yeah, they got like a pretty big speed up from for parallel querying. That was on CPUs. And then on GPUs, yeah, I don't know. I haven't thought about this at all, but it feels like you could probably do something fast. The other thing you do on GPUs, cheating, is just brute force because they're very fast to make multiplication. Um, but maybe not fast enough to beat CPUs. Um, yeah, so I think that's what I would say there. I'd say the biggest thing though is that usually it's not necessary. Usually your single threaded queries are pretty fast.
Yeah, it's so fascinating. I guess like I think because it's like a greedy search within the proximity graph, so it's like I don't see how you can because you're always following the beam, and so but maybe you could like explore the distance of like a ton of nodes at once, and so maybe it's not necessarily about parallelizing the traversal, but just like doing a bunch of distance computations in parallel or something like that. As I mentioned, I'm not too caught up, but so
Yeah, no, that makes sense. Like, I think that's very similar to what they do in this paper. Um, in like this parallel thing. And basically, yeah, you parallelize the beam in some sense.
yeah, fascinating. So, last quick question is: I see you have a paper about vector set searches, and we've started. People maybe are curious when is Weaviate going to support Colbert and this multi-vector, and so I'm really curious. Just vector set searches are these the same? Is this the same problem as multi-vector search? If you
Yeah, same problem with multi-vector.
could,
Yes, same problem. Um, yeah, no, it's a really cool problem. I think potentially, like you can get like better search accuracy than doing single vector searches. I did see this is a paper like a few days ago, probably submitted to NeurIPS about like turning multi-vector searches into single vector searches.
yep.
So you could do that. That came out of Google. Actually, Lakshman and Vahab, I don't know if you know them, worked on that paper. Maybe you come interview them. uh,
Yeah.
but yeah, I think it's an exciting area. Like I liked working on that static vector search paper, Desert. Um, yeah, but yeah, maybe these guys have now come out with something that beats Desert. So yeah, so I guess it having worked on the problem, like it feels it's a cool, very cool problem. I think it is pretty hard to solve uh, efficiently. Like Dessert does something, but it's not like incredible or anything. So I think like turning it what these recent papers on turning into single vector search is probably pretty smart. Yeah, I can actually look up. I have it right here. I can look up the title of that paper if people are curious. It's called Movera multi-vector retrieval via fixed dimensional encodings.
Super.
That's this other paper that's like builds off of like Desert and Colbert to do like multi-vector search as single vectors.
Yeah, super cool. Well, yeah, thanks so much for the shining some light on those two. And yeah, Josh, thank you so much for joining the Weaviate podcast. I'm so grateful for this experience. Just selfishly, it's been so much fun just listening to your thoughts on this and learning more about how your mind works and seeing you kind of think through things live has been so awesome. Josh, thank you so
Yeah,
much.
yeah, it was a lot of fun. Thanks for having me. Yeah.